Good day, grade 12 chemistry students. Today what we're learning about is equilibrium. Specifically, our learning goal today is we are investigating the quantitative nature of chemical systems at equilibrium and solving problems. Really all we're doing today is we're learning how to solve simple equilibrium problems that surround this, which is K. This is an equilibrium constant. I'm going to show you what it means and how to calculate it and how to solve simple problems. So take a moment to write down this question. Just pause the video right now. But what we're learning about is equilibriums. Now equilibriums, they occur in both forward and reverse reactions, okay? So they can go forward and backwards. And you can see here in this reaction we have 4 moles of N2 reacting with 4 moles of H2. It's put in a 2-liter container. They're both gases, so they fill up the container, and ammonia gas is produced. So let's determine the concentration of ammonia at equilibrium if the equilibrium concentration of H2 is 1 mole per liter. First thing you need to do, I know that's a lot of stuff I just threw at you right there, but we need to unpack that and actually write out a balanced chemical equation. Here it is. So we have N2 plus H2 equals NH3. Let's balance that quickly. So we put a 2 here and a 3 here, and we are balanced. Now what we need to know first is that if this was just in one direction and all the reactants were completely used up, what would we have in terms of NH3 over here? Well, let's write down what we have to start. We have 4 moles of N2 and we have 4 moles of H2. So let's write that information underneath our balanced chemical equation. So when we look at this, we have to determine the question, like how much product are we going to make? According to this is a 1:2 ratio. So if I have 4 moles here, we do a simple molar hop, or again using our coefficients of 1:2, we should make 4 moles of NH3. Now this is a 3:2 ratio, so it's a little bit different. So if we hop from here to here, it is a 2:3 ratio. The answer would be, if you did the whole molar hop, would be 2.67 moles. Now this is a limiting reagent type question, so again we're going to prove the lower amounts. This amount is impossible. Now this is how we would answer the problem in grade 11, but unfortunately not all equations happen just in one direction. They're not just going to continue on until products. We actually have, you'll notice that I drew my arrow kind of funny here. The reaction actually occurs in both directions. So that means we're not going to fully form 2.67 moles of product. We're actually going to go back in the other direction. So to do this, we need to form something called an ice table. An ice table stands for initial change in equilibrium. So we're going to talk about this as if not all the reactants form products. So here is our ice table set up beneath our balanced chemical equation. But now we have the double equilibrium arrows to represent that it's in equilibrium. What we're going to do in the initial part is we're going to write down the initial concentrations before anything shifted towards equilibrium. But we have to enter everything as concentrations. So it's very important that you only write concentrations in the ice table. If we look at the problem, you'll recall that it's in a 2-liter container. So for the N2 we have 4 moles and we have 2 liters. You'll recall that concentration equals moles divided by volume. So what we're going to do is we're going to take the moles, 4 moles, and we're going to divide it by the volume, which is 2 liters. And the concentration will be 2 big M, or molarity, which stands for moles per liter. You can see it's also going to be similar for H2. So let's plug those into our ice table. So initially we start with 2 moles per liter of N2 in our chamber and 2 moles per liter of H2 in our chamber, and we have 0 moles per liter of NH3 in our chamber as well. So when we look at this, the way that the equilibrium is going to shift is actually in this direction. And what I mean by shifting is I mean that these concentrations are going to go down and the concentrations of NH3 are going to go up. So they decrease by a level of 1x because it's a coefficient for every 1 N2 it reacts with 3 H2s. This will actually decrease 3x. Now my product is going to increase by positive 2x right here. These are what we call relative changes because every time 1 N2 reacts with 3 H2s, it's a 1:3 ratio. So the change is going to be much greater for H2 than it is going to be for N2. Similarly, when we compare N2 to NH3, the change is going to be twice as much for NH3 compared to N2. Now, if we look at the question further, we have a little bit more information. And here it is. It says at equilibrium, we have 1 mole per liter of H2 left over. So that means we can plug this number right here. We have 1 mole per liter of H2 left over. This means we have not reacted all of our H2. We've reacted approximately 1 mole per liter of H2. Now, do we have enough information to find the other equilibrium concentrations here and here? We do. An important thing to remember is that not all the H2 is being used up. It's not like a complete direction all the way to the right. It's going to move somewhat to the right, increasing the amount of NH3, but then it's also going to move somewhat to the left as well to reactants, and eventually we'll reach a new equilibrium and our concentrations will remain constant. So can we find the concentrations, if 1 mole per liter is at equilibrium, can we find the concentrations of N2 and NH3? Well, we can if we just isolate our one scenario here, where we have our initial concentration of 2 moles per liter, a change of negative 3x is equal to 1 mole per liter. So again, this is just simple algebra. 2 moles per liter minus 3x equals 1 mole per liter. We're going to just isolate that variable, so negative 3x. And again, we go 1 mole per liter minus 2 moles per liter. And again, so negative 3x is equal to negative 2 moles per liter. We divide both sides by negative 3. And then what we're going to get is x is going to be equal to positive 0.67 moles per liter. Now that is going to tell us the value of x. And because we know x, we now can substitute in here and we say we're starting at 2 moles per liter for one substance and we're decreasing minus 0.67, and therefore we can figure out the equilibrium value here. Also over here we have 0 moles per liter plus 2x. So that's 2 times this. We can also figure out our concentrations at equilibrium. So you can see I've just substituted in my values here where I said 2 moles per liter minus 0.67x is equal to 1.33, and 0 plus 2 times x, which is this is here, is 1.34. So we've solved our question so far. And again, in summary, we can't just assume all my reactants are going to form products because it's in an equilibrium. It goes the opposite direction. So we were given one value at equilibrium in the question, and from that we could figure out what the change was going to be and therefore find our unknown concentrations. So these concentrations again are in what we call dynamic equilibrium. N2 is still reacting with H2 to form products, and NH3 is still breaking down into forming H2 and N2, but they're happening in a manner so the concentrations remain constant. This is the easiest type of equilibrium concentration, or equilibrium question, is when I give you an equilibrium concentration in the question. For example, this one right here, it says it's at equilibrium. This is the easiest type of equilibrium problem that we are going to solve. So what is an equilibrium constant? An equilibrium constant is a constant that can describe all the equilibrium values for any given equilibrium, okay, at a given temperature and pressure, okay? So if we have an equilibrium like follows, we have Cl2 reacting with PCl3 and forming PCl5, that's equilibrium. We can get a whole bunch of different equilibrium values, and these equilibrium values will remain, at equilibrium. They're going to remain constant. Let's take a look at some. So here what we have is we have a bunch of different concentrations of PCl3. So this is one equilibrium where you have 1.4 moles per liter, 4.6 moles per liter of Cl2, and 5.15 moles per liter of PCl5. Now you have a bunch of different equilibriums that exist where these concentrations seem to be constant. And we could honestly come up with a million different types of equilibriums where the concentrations are constant. So what do all these equilibriums, share in common? Well, what they share in common is a mathematical constant. If we can take all these equilibriums and turn them into an actual equation, we can find this constant. The constant is found as follows. If we take the concentration of our product and divide it by the concentration of our reactants multiplied by each other for every single one of these equilibriums, you'll always get 0.8. Now, I'm not going to belabor the point and show you this, but every single equilibrium at this temperature and pressure will always be equal to 0.8. Now, this 0.8 tells us quite a bit. So more specifically, all equilibrium constants, when you look at the balanced chemical equation, these A, B, C, D, these are all coefficients, and they actually become exponents, okay? But really what it is product concentration times their exponent, which is their coefficient in the balanced chemical equation. So products over reactants, and their coefficient will give us our K constant. So it's best just to describe this with a reaction. Here we have H2 reacting with I2, forming 2HI. What we want to do is we've got some equilibrium concentrations here. These are all at equilibrium concentrations. And what I'm going to do is I'm going to use them to find K. So what we need to do is we need to take our products, which is HI, and we are going to divide them by my reactants, which is H2 times I2. The square brackets mean concentration. It has a coefficient of 1 and a coefficient of 1, so therefore it has an exponent of 1 on each of those. And it has a coefficient of 2, so therefore it has an exponent of 2 here. Now, to find the equilibrium constant, assuming that these values and concentrations are at some form of equilibrium, all we have to do is substitute our numbers in. So here you can see I've substituted my values in, and you'll notice I didn't include any units. K is a unitless quantity, and basically it's going to tell us a little bit about the equilibrium, but it doesn't contain units. I know that was one word. It actually should be 2 words, but there we go. It's unitless. So let's find our answer for this equilibrium. So you can see my value is 1 times 10 to the negative 4. Because this is a lot smaller than 1, this is the same as writing 0.0001. That's smaller than 1. We say that is mostly reactants because I got a lot more on the bottom. So all equilibriums will have more reactants when they have compared to products at equilibrium. So if this is our equilibrium, we have C and D over A and B. Remember, it is products divided by reactants. If you have a very large K, that means you have a lot of products at equilibrium. So all the reactants all the equilibriums that will exist are what we call product favored. They have a lot more products than reactants. If K is very small, that means you have a lot of stuff on the bottom of this reaction because it's product over reactants, and that makes the number very small. And what that means is that you are reactant favored. All the equilibriums exist will be reactant favored. They'll always have a higher concentration of reactants than you will products. We're going to put some of these ideas together further, and we'll talk about them more tomorrow. That's it for today. Enjoy your evening.